So welcome to Math 383 Complex Analysis. This is lecture 20-something. Let's see which one it is, 24. And so what I want to do today is I want to continue to review some concepts from analysis, some ways of looking at problems. And so we'll talk mostly about Stirling's formula and evaluating and as well as estimating sums. So a lot of times you have these beautiful results in textbooks where they tell you, here's a closed form expression for a certain sum. And it's wonderful when you have a closed form expression for a sum, but it's not always going to happen that you're going to be fortunate enough to have something like that. So in general, what do you do if you can't evaluate a sum exactly? Well, if you can't evaluate a sum exactly, you have to estimate it. And depending on how well you estimate it, it might be good enough. If you're Elon Musk and you're paying, what was it, $44 billion for Twitter, if it turns out that there was a miscalculation and you actually owe another, $3,000, it's not really a big deal, right? So for a lot of calculations is I want to have a good separation between my main term and my lower order terms, or I want to get a sense of what is the order of magnitude of the answer, and that might be all that I care about. And so I want to talk a lot about how to do problems like that. The goal is to build up some functions that we're going to need to understand when we want to look at the Riemann zeta function. Okay, so the first is the gamma function. So gamma of s is defined as the integral of e to the negative x, x to the s minus 1. And you can also write that as x to the s dx over x. And the reason we sometimes write it as dx over x is if I rescale x by 5, then dx over x is unchanged. And so what it's really saying is this is a function that's really nice on a multiplicative setting on the positive reals, as opposed to a translation on all of R. So there should be a reason when you see something as, why would you define it as s minus 1? That's where the minus 1 is coming from, okay? So the first thing you should always do whenever you see an object is you should prove it exists before you study it, okay? When I'm looking at this integral, do you expect this integral to exist for all values of s? No, especially since it says for s greater than 0 or real part of s greater than 0. If you're looking at that, probably we have trouble for other values of s. So when we look at this integral, what are the issues for this integral existing? So what might make this integral not exist? Endpoints. So what are the endpoints? 0. So study near 0 and near infinity. Okay. So when we're looking at it near 0, what does it look like near 0? So near 0, e to the negative x, x to the s minus 1, what does that look like near 0? So your answer can absolutely depend on s. So near 0, what does this look like? Not 1 over s. No, near x equals 0. What does the integrand look like when x is close to 0? X to the s minus 1. It looks like, 1 plus x squared over 2 factorial plus ... times x to the s minus 1 equals x to the s minus 1 plus small. When x is really small, each subsequent term in the Taylor series is going to be smaller than the previous. So the main term is going to come from the 1. When x is close to 0, e to the negative x is close to 1. So if I want to integrate, say, from 0 to epsilon of x to the s minus 1 ds, or maybe do it. So maybe I'll go from epsilon to epsilon 2. Some small interval near the origin, but not actually at the origin. What's the antiderivative of x to the s minus 1? So what is it? Are you sure? Good. If s does not equal 0, and if s equals 0, it's the natural log of x. So when we look at this integral, we want this to be finite. So we're really concerned with what happens as epsilon 1 goes to 0. So what happens as epsilon 1 goes to 0? What do we need to be true for the first one to be well behaved as epsilon 1 goes to 0? What must be true about s? Need s greater than 0. So need s greater than 0. And in fact, if it was the logarithm, it would also be blowing up here as well. So is everybody convinced that we need s to be greater than 0 if we want this to be integrable near 0? Now we need to check integrability at infinity. Okay. Near infinity, we have e to the negative x, x to the s minus 1. Okay. Are we worried about this off at infinity? No. And so one easy way to see this is the same as x to the s minus 1 over e to the x. That's going to be less than or equal to x to the s over x to the m over m factorial when x is large, right? And I can put in absolute values because why not? And now this will be less than or equal to 1 over x to the n, and we can put the m factorial here, where let's say n is going to be greater than 2 if m is large relative to s. You can figure out exactly what you need to choose, but take s, take the absolute value of s, take the first integer, say 3 greater than that. And when I do that, that's going to be enough to show that this is going to be decaying like at least 1 over x squared. So again, I'm not trying to get the best bound possible. I'm just trying to show that this function exists, that I can do the integration. So all I need is some really weak bound. And just e to the negative x, put that in the denominator. I can just keep one term that makes the denominator smaller, which makes the function larger. And this is enough to show that the gamma function exists. Okay, so yes?
Is there a reason why we define like s to be greater than 0?
Well, we need that for things to converge. We just showed that this integrand blows up if x is less than 0 near the origin.
If it's s equals to 0, it blows up. But if it's s is less than 0,
well, if s is say -1/2, you would then get epsilon to the -1/2.
Oh, then it's like
that's 1 over the square root of epsilon. That's going to blow up. Yep. So we need the function to be integrable near 0 and near infinity. Near infinity, it works for all values of s. The constraint comes from understanding what's going on near 0. Okay. So now we have the gamma function. Whenever you have something, you should start calculating terms. And I've got a couple of things written in pen on here. What's the easiest value of s to calculate this at? 1. And so if we do n equals 1, we get gamma of 1 is the integral from 0 to infinity of e to the negative x dx. That's negative e to the negative x at 0 infinity. That's the same as e to the negative x, flip the order, and that's just 1. What's the next easiest value of n? 2. And so we would have the integral from 0 to infinity of x e to the negative x dx. How do we do this? Integration by parts. And so it's not bad to just quickly review this. Let's let u equal x dv equals e to the minus x dx. Then du is dx, and v is negative e to the minus x. And I want to do it this way because if I do it this way, the power of x is getting small and it's reducing to something I know. If I tried u equals e to the minus x and dv equals x dx, then the power of x would be growing. And so when you do the calculation at the end of the day, you will get it equals 1. And then if you calculate gamma of 3, you would see that that equals 2. Does anybody know what sequence of numbers starts 1, 1, 2? I'm sorry? Fibonacci's. What else starts 1, 1, 2? Factorials. So we need more data. So we do gamma of 4, we then get 6. And at this point, it's beginning to look like gamma of n plus 1 might be n factorial. And so what we can do is, let's look at gamma of s plus 1. We can do it a little bit more generally. So it's integral from 0 to infinity of e to the negative x, x to the s, dx. So I'm going to have u be e to the minus x, dv will be, oops, did it the wrong way. U will be x, dv will be e, x to the s, sorry. Dv will be e to the negative x dx. U d goes to du, which is going to be s, x to the s minus 1 dx. V is going to be negative e to the minus x. Now, when I do the boundary terms, I've got the uv and the vu. So this is going to equal uv at 0 infinity minus the integral from 0 to infinity of v du. What is uv at the boundary going to be? When I put in infinity, clearly it's going to be fine. The exponential is going to kill the polynomial. When I put in 0, well, I'm assuming that s has real part greater than 0. So x to the s is going to vanish. So the boundary terms vanish. I've got a minus sign, and I've got a minus sign with the v. So when I have the v du, the minus sign is going to reinforce, and I will get that this is going to be the integral from 0 to infinity of s x to the s minus 1 e to the negative x dx, or just s integral from 0 to infinity e to the minus x, x to the s minus 1 dx, which is just s times gamma of s. So we've just shown, and this is called a functional equation. So gamma of s plus 1 equals gamma of s, and that implies gamma of n plus 1 is n factorial if n is a, whoops, come on, if x is a non-negative integer. Okay. So what's wonderful about a functional equation is we only have to understand the gamma function in a small sliver to get it in other places. Now, this is looking at the gamma function when the real part of s is greater than 0. We can actually use this to continue to extend the gamma function to places where the real part of s is no longer greater than 0. By saying, I'm going to define the gamma function to be the following when the real part of s is greater than 0, and I'm going to use this definition to put in value some other place. So if I want to figure out what, I dropped an s. I dropped an s over here. So if I want to figure out what is gamma of minus 3/5, I would have gamma of 2/5 equals minus 3/5 gamma of minus 3/5. Oh, I know what gamma of 2/5 is. I can now use this to deduce the value of gamma at minus 3/5. Okay, so we initially define the gamma function only when the real part of s is greater than 0. We can extend this. So long as we know the value of gamma 1 unit away, 2 units away, 3 units away, 4 units away, some integer number away. There is one value that could be hard to do. Anybody want to guess that one value that might be hard? 0. What if we try to figure out what is gamma of 0? Why is that so bad? Why is that one value causing trouble? I can do it everywhere else. Where does things break down? Okay, so I understand that the integral doesn't make sense. Yes.
You just get like 0 times.
Yes. So we try to put in s equals 0. We have gamma of 1 is 0 times gamma of 0.
You know, gamma of 0 goes up, but s is 0. So
Yes. So this actually tells us gamma, we know gamma of 0 has to blow out. So we have 0 times infinity. Are we allowed to do 0 times infinity? No, that is on our no-no list. Right? What else is on that list? I would have said rooting for the Yankees, but I'm sorry, yes. Dividing by 0, yes. Dividing by 0 is on the list. What else? Yes. Okay, what else is on the list of things you cannot do? You can't divide by 0. I'm sorry? 1 to the infinity? I think 1 to the infinity you can do. So you can't do 0 times infinity. There's another basic operation that you can't do. Nope. 0 over 0 you can't do. Infinity over infinity you can't do. What else? One other one that you're missing. I'm sorry? You're missing a really okay, you're missing a more basic one. Nope, that would just be yeah. It involves infinity and negative infinity. What can you not do to them? Infinity minus infinity. You can't do that. So there's a whole list of things you have to be very careful about doing. You always want to look and see where do things break down. And over here, if we try to do s equals 0, the problem is we have 0 times gamma of 0, so we can't get any information.
So is gamma the only function where f and plus 1 is equal to?
So there's actually a theorem due to Bohr. I think this might be I think this is the brother of Niels Bohr, which says if you have a function with 3 properties, it has to be the gamma function. And so there's a very famous theorem as to which properties do you need. Okay, so we've just established the functional equation. Can anybody give me a really interesting value of s to take? 1/2. Why 1/2?
Because it equals to, like, it has pi.
So it turns out that gamma of 1/2 is the square root of pi. This means negative 1/2 factorial. So the number of ways to arrange negative 1/2 of a person is the square root of pi. If this makes sense to any of you, I have failed as a professor. Okay, we cannot use the old notation, the old interpretation. So we can use the notation. We can't use the interpretation of the factorial function in a new regime. When we have a positive integer, n factorial is the number of ways of arranging n objects when order matters. We can extend that in other settings like this, but that does not mean that this is the correct interpretation. We lose the interpretation here. What I want to briefly remark is moments of the standard normal. So the 2kth moment of the Gaussian would be the integral from minus infinity to infinity, 1 over square root of 2 pi, x to the 2k, e to the negative x squared over 2 dx. So I'm taking my probability density and I'm just multiplying by x to the 2k. I probably should have put the x to the k in a slightly different spot. I'll just move them around. Why am I not considering odd moments? Why am I not looking at odd moments? Yes.
Can you just explain quickly what the Gaussian is?
So this is the Gaussian density. This is the bell curve. And so hopefully you've seen this before. So the central limit theorem, if you have a bunch of independent, identically distributed random variables, then their sum converges to being normally distributed. And you can figure out exactly which normal it is. So the most important is the standard normal, which has mean 0, variance 1. And so this is an extremely famous probability distribution. And calculating moments, it's kind of similar to calculating Taylor series coefficients. It's trying to get some discrete data to understand your function. Why am I not looking at an odd moment like x to the 5 or x to the 7 times this function? It's 0. I've got a symmetric function in the normal density. It's even. If I have an odd function and I integrate over a symmetric region, it's going to just be 0. So I only need to calculate this. Okay? Now, I could, of course, consider the more general case of looking at an arbitrary moment. When x is 2k, that's the most interesting one. But let's just put in, for definiteness, let's calculate the mth moment. Does this look like anything you've seen before? It kind of looks like the Gaussian. Oh, not the Gaussian, it's the Gaussian, so it does look like the Gaussian. It looks like the gamma. Now, the gamma had an e to the negative x. All right, so what should we take u to equal? X squared over 2. So x is equal to 2 to the 1/2 u to the 1/2. So du would be 1/2 x dx. Yes? Or dx would be 2 to the 1/2, and then I take the derivative of u to the 1/2. I'm going to get a 1/2 coming down. Then I will have a u to the minus 1/2 du.
Why is there still a 1/2 x dx?
Oh, thank you. Yes, du, yes, thank you. Yes, it should just be x dx, thank you. The other side, the dx is going to be 2 to the 1/2 times 1/2 u to the minus 1/2. And then that should be the same, if I do everything correctly, as 2 to the negative 1/2 u to the minus 1/2 du. If I make any algebra mistakes, please let me know.
Have the problem with balance because like
Nope. Okay, so what we can do is we can basically say, let's just go from 0 to infinity and double it. So you're absolutely correct that we have some issues. So let's go from 0 to infinity and double. So I will put these in red. We're going to go from 0 to infinity and double because we have issues with balance. And if we were only looking at m as an even number, then that would be this wouldn't be a problem right now. If m is odd, then this is a new type of integral that we're doing. Okay, so let's give this a new name. We'll call it maybe mu tilde, because it's no longer quite the mean. It is if m is an even number. So we could just consider these integrals just as functions to consider. Okay, and it turns out if m is an even number, an even integer, then this is going to be the mth moment of the Gaussian, of the standard normal. All right, so now we have to figure out what does x to the m become? So x to the m is going to become, we have 2 to the m halves, u to the m halves. So we get mu m tilde is going to be 2, and then we have the integral from 0 to infinity. X to the m is going to become 2 to the m halves, u to the m halves. We have a 1 over square root of 2 pi. Whoa. I'll pull that out. We have an e to the minus x squared over 2. That's an e to the minus u. Then the dx becomes a 2 to the minus 1/2 u to the minus 1/2 du. All right. So we have a 2 to the minus 1/2. 2 times 2 to the minus 1/2 is 2 to the 1/2. Divided by the square root of 2, that all cancels. So I think we just have a, damn it, I keep hitting that by mistake. We have a pi to the minus 1/2. We'll have the integral from 0 to infinity. We have u to the m halves minus 1/2, right? So that's the power of u. And then we're going to have an e to the minus u du. For the gamma function, what do we want to have? Did I make a mistake?
I'm just not sure how the 2 to the n over 2.
Okay, we have a 2 over 2 square root of 2 pi, and then we have a 2 to the negative 1/2. 2 times 2 to the negative 1/2 is 2 to the 1/2. We have a 2 to the 1/2 down below, so those cancel. And that's why we have a pi to the minus 1. Oh, yeah, I dropped the 2 to the m half. Sorry. Yes, sorry, I dropped the 2 to the m halves. Yes, that should be here. So we have a u to the m halves minus 1/2. For the gamma function, we want basically our variable to the s minus 1. How could we write m halves minus 1/2? So how would we want to write it? So the gamma function wants s minus 1. I have m halves minus 1/2. So add and subtract 1/2. It's m halves plus 1/2 minus 1/2 minus 1/2, which is m plus 1 over 2 minus 1. And so what you get now is this is going to be pi to the minus 1/2, 2 to the m halves, gamma of m plus 1 over 2. So we've just calculated this integral. So basically the moments of the Gaussian are related to the gamma function. If we take m equals 0, then we get gamma 1/2 square root of pi. Well, that integral should be 1 because we've normalized it to be a probability distribution. That's going to give you that gamma of 1/2, which is in some sense negative 1/2 factorial, is the square root of pi. So m equals 0 gives you that gamma of 1/2 is the square root of pi. So there is a connection between the standard normal and the gamma function, and we will see more about this later in the semester. I wanted to just point this out right now because this is an amazing connection. What I also like about this is the need to rewrite things in a way to fit what you know. Mathematicians are lazy. Whenever possible, reduce whatever you have to something you understand. We have a definition for the gamma function. We need our variable to the s minus 1. So I just rework this so that this exponent now is of the form s minus 1. I had m halves minus 1/2. Okay, it's almost there. The other thing was the change of variables to e to the negative x squared over 2. If I call that u, then I can fix the exponential there. I'm going to change the power x to the m. I'm going to change that, but I'm going to change it in a way that's very easy to work with. Okay, and so this is just writing things out in general. It turns out there's a really nice formula. Yes? Because this product is equal to 1. So we have a pi to the minus 1/2 times gamma of 1/2 is 1. So gamma of 1/2, I move the square root of pi over. Yep. And so if you take m to be an even integer, it turns out that there's a really nice expression, and you're going to get nice numbers called like double factorials. Right? I'm not going to go into too much more detail about that. What I want to do now is I want to remark on one of the most important results we have about the gamma function, Stirling's formula, which describes what happens as you let n go to infinity. So can you talk about the limiting behavior? And of course, we don't want to discriminate in this class. Rather than restricting n to being an integer, we might want to allow n to be a complex number and still have some type of expansion for what does gamma of s look like for large values of s. Sometimes rather than studying gamma of s, we might study the log of gamma of s. And there are expansions for that as well. So this is telling us that n factorial is about n to the n e to the minus n square root of 2 pi n. Does the square root of 2 pi surprise you now? Hopefully that shouldn't surprise you after what we saw before. Sometimes there are coincidences in mathematics, sometimes there are not. There really is something deep going on that's connecting the gamma function to the Gaussian. All right, and in fact, we even have a Taylor series approximation. Does everyone agree Elon Musk is rich? If you took 1/12 of his money, that's a lot. If n equals 100 and you took 1,000 of his money, that's still a lot. So in terms of the actual size of the term 1/12n times the main term, that could still be a tremendously large term. It's just when n is large, it's going to be much smaller than the main term. On an absolute scale, it might be very large, but relative to the main term, it's very small. And so when I'm trying to see what is the size of the object, the main size is going to be dominated by the first term. That doesn't mean that the other terms aren't small. It just means that they're much smaller than the main term. And as n goes to infinity, it's going to be much lower order. Okay. So I want to do some crude upper and lower bounds. I don't care how bad the bounds are. Can somebody give me a really bad upper bound or lower bound for n factorial? N to the n, right? Clearly, it's at most n to the n. Can somebody give me a really bad lower bound? 0. A little bit better. N, right? So we know it's somewhere between n and n to the n. Now, if you look at Stirling, what was Stirling saying? Stirling was saying it's n to the n e to the minus n squared of 2 pi n. So it's a little bit less than n to the n, exponentially less, but n to the n is growing so much more than e to the minus n is decaying. That upper bound is not so bad. It's sometimes worth just going through the algebra and seeing what would be the consequences. What would happen if we tried to apply Stirling's formula? If we take n plus 1 factorial by Stirling, that would be n plus 1 to the n plus 1 e to the negative n plus 1 square root of 2 pi n plus 1. And now let's divide by n factorial, which is n to the n e to the minus n square root of 2 pi n. So when I look at this, I can write this as n plus 1. I'm then going to have n plus 1 over n to the n. So that's going to be 1 plus 1 over n to the n. E to the negative n plus 1, e to the negative n, that's just going to give me an e to the minus 1. And then square root of 2 pi n plus 1 over square root of 2 pi n, that's going to give me a square root of n plus 1 over n. And then as n goes to infinity, what does this look like? So this is going to go to e. What's n plus 1 over n square root going to go to? 1. So this is looking like n plus 1. And there's the proof of Stirling. So is this a proof of Stirling's formula? No, this is just showing that Stirling's formula is consistent with what has to be true. We know n plus 1 factorial is n plus 1 times n factorial. So Stirling damn well better give us something like that. And we are seeing that it's at least consistent. So whenever possible, if you can ever do quick, simple tests to get a feel for what's going on, that's great. Okay, we still need to get the right size. We still need to prove Stirling. But this is at least telling us it's reasonable. All right, how many of you remember that you were supposed to have learned the integral test? How many of you remember the integral test? Okay, and this is why we're spending time doing some analysis and not just moving forward. The integral test is absolutely wonderful. And it's a way to get a pretty good, quick estimate of Stirling. So by now, you have had enough lectures with me this semester to know that whenever you see a product, you take a logs. And if you find that you're teaching 4th graders multiplication, you realize you made a mistake. But other than situations like that, it is a good idea to take logarithms when you see products. If we take the log of n factorial, it's the log of 1 plus the log of 2 all the way up to the log of n. Oh, that's like a Riemann sum. It's the sum of log k. And so we can try to estimate the sum by an integral. And the way the integral test works is, imagine you have a sequence which is non-increasing or non-decreasing. And you have a nice function that goes through those values. You can then approximate the sum by the integral. And so let's look at what's going on over here. So over here, if I look at the reds, the blue is a little bit over. So the area under the curve would overestimate what's going on for the sums. If I look at the other one over here, it might be hard to see the blue line, but actually, I can just draw over the graph. Excellent. So hopefully that's that's a little bit easy now to see. And so if I go this way, it all comes down to, am I taking my value when k equals 1 and moving to the right from 1 to 2, or am I moving to the left from 0 to 1? And so in one way, the function is going to overestimate. In the other way, the function is going to underestimate. They'll differ by like the first and the last piece. And so if I look at this, if I take the sum from 1 to n of log of k, I claim that's less than equal to the integral from 2 to n plus 1 of log of t. And so what I'm doing now is I have 1 going from 1 to 2, from 1 to 2, and that's going to be below the value of the function from 1 to 2 because the function's increasing. And so my last thing is going to go from n to n plus 1. Okay, so we should get something like that. And then conversely, we can get a lower bound by going the other way. Does this bring back memories now? And you can often use this to prove, the sum converges. If the integral converges, the sum diverges if the integral diverges. And you can be even more careful, and you can say, how much do they differ by? And you can often play things so that they differ by like the first and the last term. Okay, does anybody know what function has derivative log t? Almost. Almost. T log t minus t. So how would you get that it's t log t minus t? What you could do is you could, guess maybe the derivative of t log t. Let's look at that. If I take the derivative, I get 1 times log of t minus t times 1 over t. That's the log of t minus 1. Oh, that almost gives me what I need. I need the log of t. I have the log of t minus 1. Can anybody give me a function whose derivative is 1? T. So now if I do t log t plus t, and I take the derivative of that, I will now get log t. As an aside, you can then try to figure out, is there a nice function that has derivative log squared, log cubed, log to the 4th? And often, by having some idea of what to guess, you can then refine the guess. We can now plug that in, and after you do a little bit of work, you get that, n factorial is about n to the n e to the minus n times e. That's not bad. We're getting the right power of n. We're getting the right exponent of e. We're missing the square root of 2 pi. Now, as an aside, the danger is the first and the last terms. So what the first term is 1. What's the last term? When we're looking at the product, what's the last term in n factorial? N. What's the average? Nope. Yes, square root of n. There's more than one average. N plus 1 over 2 is the arithmetic average. I want to use the geometric average. The geometric average is you multiply the numbers and take the square root. The geometric average is more appropriate here. The arithmetic average would be correct if we did it on a log scale. And we look at the log of 1 plus the log of n. Take the average of that. If we do log of 1 plus the log of n over 2, that's the log of n halves. And then when you exponentiate, you get up to this as well. And that's roughly where that extra square root of n is coming from. It's basically splitting the difference in terms of what the other, not a proof. Okay, but it's giving you a rough sense that if I had to guess, I would guess that I'm off by a factor of square root of n. That would be my guess from just doing some quick calculations like this. Okay, so there's what's called the Euler-Maclaurin formula. If you do number theory, it's worth knowing a formula like this. So I'm just leaving a link here. The more derivatives you know about the function, the better you can do approximating it. And you can replace sums with integrals. And so what we're seeing here is really just the first of many different types of results you can get. Okay. Everybody should hopefully have seen the sum before. How do you prove this? Induction. So what I want to do is I want to not necessarily prove it. I will actually have a couple of slides, and I'll link to the talk from previous years about how you can actually prove this for certain values of n by recursion. I want to try to get a sense of the order of magnitude. So let's call this sum S2 of n. No, S1 of n. Okay, can somebody give me an upper bound for this? It's okay if it's really bad. Good. S1 of n is clearly less than or equal to n squared. Can you give me a lower bound? Lower.
0.
Okay. Little 1. There you go. All right. Now we can correct that 1 up to an n. Okay. So the question is, what is the true order of magnitude? My trivial lower bound is of size n. My trivial upper bound is of size n halves. Can somebody give me a lower bound that's better than n and of the same size as n squared, or an upper bound that's of the same size as n? And given that we know that it's of size n squared plus 1 over 2, I think you know if you want to try to increase the lower bound or decrease the upper bound. Can anybody give me a better lower bound? Not n log n.
N over 2 times n.
N over 2 times what?
No, n over 2 squared.
N over 2 times n over 2. That's a terrible 2.
Because you can match the numbers.
Yeah, because if you just look at 1 plus 2 plus dot 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 plus n halves, and again, I'm not going to worry about whether or not things are exactly integers, then you have n halves terms, each at least n over 2. So we know 1/4 n squared is less than or equal to S1 of n is less than or equal to n squared. I don't have the correct constant. I don't know what that is yet. What's the average of 1/4 and 1? 1/2 if you average them geometrically, and that is the answer. So is that a coincidence? I can't give you every single time answers that are always the same way, or you'll. So is it a coincidence that the average happens to be 1/2? So at this point, we have the correct order of magnitude. So we have the correct growth rate. And for many problems, that's what really matters, is to try to sniff out how do things depend on the main parameter. Okay, I'm not going to go through the details. I'm going to just leave it posted here. I'll give you a link to the video. I tried to set up a recursion relation using the great result that if you split into evens and odds, well, the sum of the evens is just twice the sum of all the numbers at the half level. And the sum of the odds, if you just shift all the odds down by 1, you get the evens. And so you can play some games. I'm going to let an be the sum from 1 all the way up to 2 to the n. You can get a recursion relation. You can actually solve it. And at the end of the day, I think I was able to get the formula that we wanted. So I will just leave these slides here for you to play with. At the end of the day, some of this might be intelligent guessing that I think it might be a polynomial of the form something n squared plus something n, and just playing games like that. Okay. What I want to do is I want to apply this a little bit to Stirling's formula. So this is called dyadic decomposition. Have you seen this in any of your real analysis classes? Okay, I'm really glad that we're doing this. This is an incredibly powerful trick. You keep breaking things in half, you get your bounds, and you keep breaking in half, breaking in half, breaking in half. In the interests of time, I am not going to worry about the fact that n might not be divisible by 2. We're not going to worry about stuff like this. I'm just trying to give you high level what's going on. I could do upper bounds and lower bounds. I'm only going to worry about doing upper bounds. Okay? Lower bounds would be very similar. All right, so let's split the numbers from 1 to n into 2 sets. The numbers from 1 to n halves and the numbers from n halves to n. So what can you say for the bound of the product? The product is what? Less than or equal to not n squared over 2.
N over 2 times n.
No, it's n over 2. What's the product? Each term is, I want an upper bound. I want an upper bound. So the upper bound is n. I'm bounding each term by n to what power? How many terms do I have? N over 2. So the product is at most n to the n halves, right? Right, product is, now if I wanted a lower bound, what would the lower bound be? It would be n over 2 to the n over 2, right? So we can calculate upper and lower bounds without too much trouble. Now over here, what's the product? It's less than equal to n over 2 to the n over 2. So n factorial is going to be less than equal to n over 2 to the n over 2 times n to the n over 2. So it's going to be 1/2 to the n over 2 times n to the n. Or 1 over square root of 2 times n to the n. Okay, so if I calculate 1 over e, I get 0.36 roughly. If I calculate 1 divided by square root of 2, I get 0.707. Yes, did I make a mistake? Oh, yes. Oh, sorry, the exponent should still be here. And in fact, what I want to do is I want to write this as root 2 to the negative n. Oh, sorry. Okay. So what I want to do, I dropped the n, I'm sorry. So it's the same thing as the square root of 1/2 to the nth power. So that's going to be the same as root 2 to the negative n times n to the n. And I'm comparing this to, it's supposed to be e to the minus n, n to the n. So actually, I'm doing it the wrong way. So instead of 1 over e, I should be having e, which is about 2.7. And I've got the square root of 2. Which is 1.414. What should we do now to get a better upper bound? Keep dividing, lather, rinse, repeat, shampoo mathematics, right? We have 1 to n over 4. And again, I'm just going to write, casually here. I know there should be plus 1s and all that, but come on. 3/4 n. And then I'm going to have 3/4 n to n. And instead of writing it as n halves, I'm going to write it as 2n over 4 so that I have the same denominator everywhere. Okay, so for my upper bound, it's going to be less than equal to n/4, I'm sorry, to the n/4. And then the next range, it's going to be 2n over 4 to the n/4. Then it's going to be 3n over 4 to the n/4. And then it's going to be n to the n/4. So when I put everything together, I'm going to get 1/4 times 2/4 times 3/4 to the n/4 times n to the n. So it's going to be 4 times 4 is 16 times 4 is 64 divided by 2 is 32. So it's going to be 3 30-seconds. Yes? Or 32 thirds. Take the 4th root of that, and that's going to be to the negative nth power n to the n. So I need to just calculate what is the 4th root of 32 thirds. (1.8). So getting closer to e. What do you think will happen if we take more and more of these decompositions? Yeah. So my challenge to you is, can you actually prove that this will converge? So we will prove Stirling's formula later in the semester. What I wanted to do today was talk about how to think about problems like this. Without being able to solve, we're seeing that it's looking like some constant to the minus n times n to the n. And we're able to get that really easily. So the next few slides just go through a analysis of this, just doing a couple more cases from a textbook I wrote a couple of years ago. So I'm just quickly putting them up here, just because this way you can now hit pause on the YouTube video if you're ever looking at this later. But the slides are also going to be publicly posted. So you can go through and you can see how far can you elementally push arguments like this. Okay, so this is a good place to stop.